Today I want to talk a little bit about the difference between the strong acids and the weak acids. And I've talked in previous videos about kind of the definitions of them, which I've sort of reminded you of here, that strong acids have complete dissociation of the ions, really. So something is acidic when it donates a hydrogen or puts a hydrogen into solution, kind of depending if you're thinking Bronsted-Lowry definition or the Arrhenius definition. But that complete dissociation means that it's a strong electrolyte, meaning that there's lots of ions in solution and therefore the solution is going to conduct electricity well. A weaker acid is something that only partially dissociates, so it's still going to exhibit acidic behavior, meaning it's still going to dissociate. I'm going to put that hydrogen into solution, I'm going to donate that proton. But because it's weak, it really doesn't do it as much as a strong acid would. It only partially dissociates, thereby most of it staying kind of together. Hence the weakness, right? We have to stick together when we're weak. And that means that we have kind of a solution that still conducts because we still have some ions in there, but it is only weakly conducting because there are fewer than with a strong acid. So the difference then in the neutralization process, it's still the same process. An acid and a base, when I react them together, whether it's strong or weak, is still going to give me a water and a salt. But the net process, the net ionic process, that kind of take-home message of your chemistry, right? If we're thinking about it like pay, net versus gross pay. So we're going to have my kind of take-home message of my chemistry, which is really like the cool part. Why do we care about this chemical reaction? Well, we care about it because of whatever that net process is. And that's going to look slightly different for strong versus weak acids. So let's take a strong one first, and then we'll look at the net ionic equation. So in both of these, I'm going to use a strong base reacting with either a strong acid or a weak acid. So let's start with strong. Let's look at hydrochloric acid. We know that's a strong one. And let's react it with calcium hydroxide, which is a strong base. And we know that it's strong because all of the metal hydroxides from the metal cations coming from groups 1 and 2, so the alkali metals and the alkaline earth metals, except for beryllium, are strong bases. Now we know that the hydrogen from my acid and the hydroxide from my base are going to form water. And then the salt that forms is going to be the calcium, the cation from my base, and the anion from my acid. So it'll be calcium chloride. Charge on calcium is 2+, chlorine is a 1-, so I need 2 of my chlorines for every 1 calcium. And if I look at my solubility table, then my chlorides tend to be pretty soluble. Now am I balanced? It looks like I'm not. I got 2 of them there, so I need 2 of them here. 2 hydrogens and 2 hydroxides mean I need 2 waters. So when I do the total ionic equation, recall that if you've learned stuff about precipitation reactions, that you need to separate everything into its component ions. So this guy's going to be separated into 2 H+ and to 2 chlorides. And this one's going to be separated into a calcium 2+ and 2 hydroxides. And I know I can separate them because of the form that they're in. Aqueous or aqueous means that they're surrounded by water molecules. They're dissolved in there. So my total ionic equation is going to be the sum of all these ions that are swimming around in solution. Now, a liquid is going to stay as a liquid, right? That's not going to dissociate. It's a molecular compound. And then, again, I have an aqueous compound, so this guy's going to separate into its component pieces. And now if I'm looking at my spectators, because I want to get rid of the things that are in common on both sides, then I can see that I can get rid of my calcium ions, because I've got 1 on each side. I have 2 chlorides on each side. So my net, my kind of take-home message here is going to be that 2 of my hydrogens react with 2 of my hydroxides to give me 2 waters. And it makes sense that this would be the take-home message from this reaction because it's a neutralization reaction. I went from something that has a low pH with a large concentration of hydrogen ions to something that has a high pH with a large concentration of hydroxide ions to something that's there in the middle around 7 with my water. So that's a strong acid. Now, how would this look different if my acid didn't completely dissociate, if it didn't split apart? Well, let's look at that. Let's take a weak acid. Let's take HNO2. We know that it's an acid. It's got a hydrogen. It's attached to a polyatomic. This polyatomic is nitrite, so this would be nitrous acid. So I'm going to react nitrous acid with, let's do sodium hydroxide this time. Make a nice 1 to 1 to 1. Sodium hydroxide is a strong base. Again, I know that because sodium comes from the alkali metals, so any of those first group paired with the hydroxide are going to be strong. That's a neutralization reaction, so the hydrogen from my acid and the hydroxide from my base form water. It's liquid water. And then the nitrite ion and the sodium ion are going to form an ionic salt. That's what a salt is, an ionic compound, a crystalline compound. And it's going to be aqueous or aqueous, I know, because of my sodium, right? Nitrite is also quite soluble. Okay, so if I'm thinking about this in terms of a take-home message, this guy's a little bit misleading. It does dissolve, but what I know about nitrous acid is that it is weak. And so even though it's soluble, most of it is going to want to stay as HNO2. So it's not going to dissociate. It's only partial dissociation. So it's going to stay stuck together because of the weak acid behavior. So because it's weak, we're going to keep it all in one piece. Now the sodium hydroxide is a strong base, so it's going to dissociate into its component ions. There's my hydroxide. And then I'm still going to get water, and water is water. Liquid. Some of this hydrogen is going to form some of this water. And then this guy is soluble, so I end up with a sodium ion and a nitrite ion. Okay, so the key to this one, the reason this is different is because of this weak behavior of my acid, I'm not going to completely dissociate. So we're going to keep that stuck together. All right, now let's look for our spectators. The only thing that's in common on both sides is going to be my sodium ion. So when I get rid of my spectator ions, then my net process is going to look different for the weak, because now I have some of my weak acid present. I have some hydroxide that's still reacting in there with some of that hydrogen. Whatever hydroxide can get its hands on whatever this hydrogen is going to form some water. And then I'll be left with a nitrite ion as well. So it's messier, is what I'm trying to say. And because I don't have as many ions on the product side, there are some ions here, but these ions are reacting. This is going to be a messier process, and we'll actually get into this kind of behavior, this weak acid behavior, which can reach a state called equilibrium in later videos when we talk about equilibrium and equilibrium constants. But for now, what I'd like you to hear and what I'd like you to see from this is that the difference in the strength of the acid and the way that it dissociates in solution is going to allow for a different environment, right? Kind of a different product environment for each of these scenarios, depending on how much and how well these acids dissociate. So that's why it's important to know the difference, because you're going to have slightly different take-home messages for the different processes.